Any other questions on that, let me know. Otherwise, let's just get started. And I say that because all I'm going to do is go through a bunch of reviews. And I know I made a couple of little tweaks here and there, but the answers to all of these questions will be open this afternoon like it normally does. Whatever I don't finish today, I will be here on Thursday. Excited to be here as always. So I hope you come as well. It is totally up to you. The idea is to have any questions you want to bring, I will just work on them. That'll be the first thing. You can ask me a question, test me, stump me, try to do something. It doesn't take long to make me show that I don't know what I'm talking about. So anyways, you can try to stump Larry. That's fine. I will answer your questions. Beyond that, then I'll just finish up with what I don't finish today. I'm not going to rush through these necessarily. It's quite a few questions, and we'll cover what we cover. And whatever I don't finish today, if I got time on Thursday, I'll finish them up on Thursday. All right, so let's start with the A word, and by that I do mean aliquot, right? So let's deal with this question here. It says, you need to weigh 45 milligrams of a drug substance using a prescription balance with a sensitivity requirement of 6 milligrams and an acceptable error of no more than 5%. And then you can use lactose as your diluent to make the actual aliquot. All right, so an aliquot is a type of calculation you perform when you need to weigh less than you can accurately weigh. In this case, we want to weigh 45 milligrams. Can we accurately weigh that? So the first question is, letter A says, well, what is your least weighable quantity? Given the sensitivity requirement of 6 milligrams and 5% error, what is the least amount we could weigh? Were you guys able, do you remember that? What was the formula? Sensitivity requirement times the 100 divided by the percent error. So if you took 6 milligrams times 100, that's 600. Divide that by 5, what do you get? 120 milligrams. So that's the dilemma. We only want 45 milligrams of drug, but we can't accurately weigh that on our scale. Given the precision, we can't really weigh less than 120 milligrams. So what are we going to have to do? Can we weigh 45? No, we have to weigh more. So the trick is to find the least whole multiple. So we're going to have to try to figure out, well, if I want 45, how does it relate to 120? If we weighed twice as much, instead of 45, what is 45 times 2? That'd be 90, right? Could we do that? No, we can't do that. So what I'm getting at is the next question says to determine how the required amount using the smallest value for the multiple and the least amount for the actual aliquot. Okay, and so in the end we're trying to solve for the amount of lactose. I just said we can't double the 45, that would only be 90. What if we tripled the 45? What would 45 times 3 be? That would be 135. Is that greater than 120? Yes, so the least whole number multiple would be 3. 2 is not enough. You could go higher, but the least number would be 3. Okay, so that's our multiple. Our multiple will be the number 3. So to do that, take the multiple number 3 times the amount you want, which is 45, and say, okay, the amount of drug I need out of this will be 135. I'm going to have to weigh back out 135 milligrams. Okay, of what though? I need to make a mixture. All right. So your mixture has to be 1/3 the concentration, right? So instead of pure drug, it has to be 1/3 pure drug, all right? So what is the least amount I can weigh? What did we say? 120. So take the least amount you can weigh and multiply it times that multiple. What did we say the multiple was? 3. So what is 120 times 3? That's 360. That's the mixture I have to make has to have a total weight of 360 milligrams. Of that weight, how much will be drug? What did I say? The least I could weigh of drug would be 120. So if I take 120 milligrams of drug and subtract that from 360, then the difference is the amount of lactose I have to add, which is 240 milligrams. Okay with that. So 360 my total, which is 3 times my least weighable quantity. 3 times 120 gave me 360. Subtract the 120 for my drug gives me 240. All right? That's your answer for the question in that case. The amount of lactose to mix is 240 milligrams of lactose. That's the least amount of lactose I would need. All right? So let's verify that. So let's do this thing down here. Does that really work? How much drug did I say I was going to weigh out? Of drug, pure drug, I was going to weigh 120 milligrams. That's my least weighable quantity. I mixed that with 240 milligrams of lactose. What would be the total weight of that mixture? The total weight of that mixture would be the 360. So are you okay where those two numbers come from? 120 milligrams of drug will be mixed in with 240 lactose and give me 360 milligrams of mixture. Once I have that mixture, what do I do with the mixture? Do I need all of that mixture? I only need the mixture that gives me the 45 milligrams, which we said was going to be the 135 milligrams. So if I weigh the 135 milligrams, which I'll remind you came from the multiple times our desired amount, so that's the amount of mixture that I weigh out once I've made it, then if you do that math, you'll see that mixture is only going to contain 45 milligrams because it's only 1/3 pure drug. So what it essentially, anyways, that's the idea behind it. Questions about that? I know you've done this before. It has been a little bit over time, so I wanted to review that process. Hopefully that kind of makes sense in terms of the way we kind of ask that question is the least whole multiple and the least amount, essentially, of the aliquot. Okay? All right. Well, let's move past that. And these rest of these questions are kind of in random order. I'm not going to go chapter 3, 4, 5 and kind of through there. They kind of go through and kind of mix some of these things here. So let's start with the isotonicity because, again, it was about 50-50 on the last quiz. Half of you got it right, half of you didn't quite get it right. So let's make sure we can do this. And there are several steps along the way here. So essentially, we have a formulation. If you look on the prescription, we have 3 ingredients. We want some tetracaine, epinephrine, and cocaine. And we're going to mix all of those together and make a nasal spray. And they'll oftentimes do that, even with the cocaine. You're thinking, what? That's also for ENT surgery. When they do surgery, especially with the nasal cavity, there's a lot of blood vessels, there's a lot of bleeding. Cocaine actually is a very strong vasoconstrictor, so sometimes they'll use that. And those of you who work in hospitals, you have it in your narcotics cabinet. So anyways, with that as a background, we've got 3 ingredients, and we're trying to make a nose spray, essentially, for this surgery, and a total volume of 30 milliliters. Okay? You guys kind of get that? We got concentrations, we got a total volume of 30 milliliters, and I provide you the E-values. We'll come back to the E-values here in a little bit. First question says, you need to prepare 30 milliliters of this formulation. How many grams of each of the 3 active ingredients will be needed? This is simply just a concentration of volume times the concentration to determine that. Watch your units, and remember, concentration can be expressed in different ways. So if we start with just the tetracaine and look up on the prescription, we know it was given to us at 0.75% weight per volume. That means 0.75 grams per 100 milliliters. So I set that up. Multiply that by the amount that we're trying to make, which was 30 milliliters. Milliliters will cancel. And I'll end up with grams. And if you do that math across, pretty straightforward, you get 0.225 grams. That easy, I hope? Very strong skill you should hopefully have at this point. The only other little trick to the next one is epinephrine was given to you as a ratio strength. So as instead of a percent concentration, I told you it was 1 to 4,000. All right, maybe that was creepy early on in the semester, but now that's no big deal, right? Ratio strength, essentially, in this case, a weight per volume is just going to be in grams per milliliter. So 1 to 4,000 means 1 gram per every 4,000 milliliters. So you just set it up that way. Again, you multiply by your volume, so milliliters cancel, and you would get grams, in this case, still, of your epinephrine. And the cocaine works the same way as before. 3% means 3 grams per 100 mils. Multiply that by 30 mils so that, again, units cancel, and you get weight in grams. Okay? Hopefully that was easy. We're going to need those numbers. That wasn't supposed to be a hard part of the calculation, but we're going to need those here in a little bit. Let's go the next step further, because it says you have the following actual solutions on hand. Now we know the weight of the drug that we need. We're going to get those from a formulation where it's already in a liquid format. So the tetracaine comes in a 2% solution, the epinephrine's a 1 to 1,000, and the cocaine is a 0.6%. So the next question asks, what volume of each of those ingredients will you need to provide the amount of drug? So starting with the tetracaine, we're following up with our answer from previously. We said we've determined 0.225 grams of tetracaine. So let's essentially multiply it by the concentration above here. Re-express, so we know it was 2%. So if we bring back down, 2% essentially means 2 grams per 100 mils. But we'll set it up this way so that if we multiply this way, the grams will cancel. And I will get milliliters. And so that value multiplied across gives you 11.25 mils. Again, epinephrine, we'll just start with the weight that we needed. Remember now, our concentration of our solution is 1 to 1,000. So we'll just set that up. Remember, ratio strength is 1 gram per 1,000 milliliters. So we just set it up so that grams cancel again, and we get our milliliters by multiplying across like that. And cocaine works just like the tetracaine. It was 0.75 6% solution, meaning 0.6 grams per 100 mils. Set it up so that grams cancel, and I get milliliters. All right? So, do you know the volumes of each of the additives we need to get the desired amount of drug? We've just calculated that volume. The question was the amount of water, though. So how do you determine the amount of water? Simply take the total amount we wanted to compound. That was the amount of each of those drugs for what total volume? A total volume of 30 milliliters. So remember, this is what we're trying to make, is the 30 milliliters. So the amount of water we're going to have will start with the 30 milliliters and subtract each of the individual ingredients. You subtract them all out and you get a total of 9.75 milliliters. Okay on that? These were still some fundamental stuff. Now we're finally getting up to the isotonicity question. It asks how many milligrams of sodium chloride would be needed to make the final solution isotonic. Because we could make the solution. You could have all of those volumes, add the remaining amount of water, squish it all together, and you've got 30 mils, and every single drug concentration would be perfect. Why couldn't you use it? Because it would cause irritation in the nasal passages that are very sensitive. So we want to make sure the final solution is isotonic or compatible with biologic tissue. So let's add some additional sodium chloride to make sure it is isotonic. What values did I give you for isotonicity calculations? E values. E value stands for what? The sodium chloride equivalent. All right. So let's use those E values and go. And essentially the target here is using the E values. We know how much drug for each of those, but we need to determine how much sodium chloride that amount of drug is equivalent to, okay? So let's start with the tetracaine. We know from our previous one that this is the weight of the tetracaine that we're going to have in our solution. We look up here for our E value. We can come down here and say, okay, let's re-express 0.18, and I remember this from a calculations class. That means 0.18 grams of sodium chloride per gram of drug. So I can set it up with that kind of proportion with those units, and if I multiply it like this, that way grams of tetracaine cancel, and I get grams of sodium chloride. And lastly, just convert that to milligrams by multiplying by 1,000. And what I've said is 0.225 grams of tetracaine is equivalent to 40.5 milligrams of sodium chloride. Is this familiar? A little bit. That's all we're doing is taking the weight of our drug and finding the equivalent weight of the sodium chloride that it mimics osmotically. Let's just do the same thing for the other two ingredients. So I won't belabor the point, but you start with the weight of your drug. And again, the weight of the drug in grams. You then take the E value. So here's the E value for epinephrine. I'll bring it down here and set it right in there. There's the 0.29 grams of sodium chloride per gram of epinephrine. That way epinephrine grams cancel, and I'll be in grams of sodium chloride. Lastly, for the cocaine, if I take that value, bring it down here, I'll take the weight that we wanted, the 0.9 grams of cocaine times 0.16 grams of sodium chloride per gram of cocaine, and I'll convert each of those into an equivalent weight of sodium chloride that those drugs mimic osmotically. Great, we got the sodium chloride. Is it enough? How much do we need? We know how much is there now. What's our target? Tell me this. Ask yourself internally. Do you know what an isotonic concentration of sodium chloride is, right? 0.9%. So all you need to do is multiply the 0.9% times whatever volume you're trying to compound. In this case, it's 30 milliliters. So essentially 0.9 times 30 milliliters, converted to milligrams, is 270. So that's my target. That's the total amount I need. So the last step is simply to take that target, bring it over here, and subtract each of the individual ingredients that we just calculated. The difference between my target of 270 milligrams and each individual drug ingredient means I still need 83.32 milligrams of sodium chloride. All right? And if I have solid sodium chloride, I just weigh that and use that. And that's kind of what we're doing in this example here. Questions on that? What was the other method? Wasn't there another method? Yes, could you do this, the same exact prescription here, but let's do it now. What if I had provided you the delta TF 1%, the freezing point depression method, okay? So in this question, and we're going to do the same thing. We got the same ingredients at the same amount, but instead of sodium chloride, I'm telling you to use boric acid to make the final tonicity adjuster and to use the freezing point depression method. I personally think this method's a little bit easier, because here's why. You can leave with things in percents. If you've got your concentrations in percents, you can start with that. So let's just look, don't ignore right now, I put it all up at once, but let's just look at tetracaine, okay? Because here's my concentration as a percent weight per volume, okay? Here's my delta TF at a percent. I know my freezing point depression is 0.11 degrees for a 1% concentration. So let's start with that. So I'm going to bring that over to here and just set that up as a proportion, saying 0.11 degrees Celsius per a 1% concentration. Does everyone see where the 1% comes from? It's a 1% given right there in the formula there. So that's what I know is standard for tetracaine. The concentration I'm going to have in my prescription is 0.75%. So 0.11 degrees over 1% is equal to X degrees over my 0.75%. I can proportion out and see how many degrees I would reduce it given my concentration. And for me, for tetracaine, it's 0.083 degrees Celsius. I won't belabor the point, but you do the exact same thing for the other ingredients. Just remember that a 1 to 4,000 ratio strength is the same as 0.025%. Just take a 1 divided by 4,000 and convert it to a percent. So that's the same number there. But really, those work exactly the same. So are there any questions on how I got that? I don't want to rework all three of those. You just take the percent and take the 0.17 over 1% equals X over 0.025% for the epinephrine, for example. Well, that's all good again. I know how much each individual ingredient lowers the freezing point depression, but here's a little bit of a trick, and I probably provide this to you on the test, but do you remember what an isotonic solution freezes at? What's the depression value we've talked about before? Remember how you memorize 0.9%? That is important. You got to know that one. 0.52. So remember, the target is a depression of 0.52. That's just what an isotonic solution freezes at. So if we take 0.52 degrees and subtract every single ingredient, then what's left is what I still need to get. So when you subtract all that, then it turns out this is what I still need to get from my boric acid. So I need 0.163 degree depression. So how will I do that? Well, I was given let me change my color here. I was given this information for boric acid. Now I don't know its percent, but I know the degree of depression I need. I need 0.163. So let's just set that same proportion up. 0.29 degrees over 1% is equal to, now I know what I want. I want that amount of reduction over X, and X will be the percent concentration of boric acid that gives me that reduction. All right? So by solving for that, I found out that I need a 0.562% concentration of boric acid. Last step to actually figure out how many milligrams of boric acid is just to take that percentage consideration with the volume I'm making. So remember, I want 30 milliliters. So if I start with 30 milliliters and I multiply it by that concentration expressed in grams per mil, so that milliliters cancel, and then just convert it to milligrams by multiplying by 1,000, I determined that I need to add to my 3 drugs, I need to add an additional 169 milligrams of boric acid to make it isotonic. So on the test, these two questions, or one of these two, or I can't remember how many I told you to be on. I think there was only one isotonicity one listed on there. It could be either one of those. So remember, I give you a prescription. You take the ingredients, you figure out how much tonicity those ingredients are contributing, whether it's through sodium chloride or for the freezing point depression method. Find the difference. Use whatever additional ingredients you have, sodium chloride, boric acid, whatever it is, to make up the difference. All right? Questions? Okay, let's move on. All right, so we've got another prescription here, and this is a veterinarian product used for cats and dogs. I think it's for dogs, it's listed there as dogs. So it's got some active ingredients. It's got an antibiotic, Gentamicin, betamethasone, which is kind of a steroid, anti-inflammatory, and clotrimazole, which is an antifungal agent. So it's got all sorts of different things. Tetracaine, again, is kind of the anti-local anesthetic for pain and discomfort. And we're going to add all of those ingredients up and some propylene glycol and essentially make this ointment with a total weight of 100 grams. Okay, so all of those weights with additional ointment base up to a total weight of 100 grams. To this first part of this question, the thing you got to realize, though, is gentamicin comes as gentamicin sulfate. Okay, think of it as a moiety versus a compound. The moiety in this case is gentamicin. The compound is gentamicin sulfate, because the additional information I give you is that based off of the commercially available gentamicin sulfate, that sulfate has essentially the potency of 590 micrograms of the base, that is the moiety, per essentially milligram of the gentamicin sulfate. So in 1 milligram of gentamicin sulfate, that's equivalent to, and can you guys convert micrograms to milligrams in your brain? 590 micrograms is how many milligrams? How many decimal points is 1,000, right? So what's 590 divided by 1,000? 0.59. So I'm just trying to, 1 milligram essentially of the sulfate has 0.59 milligrams of the base. All right, you'll see that here in a minute, because it wants to know how much gentamicin sulfate would be needed to prepare 30 grams of this formula. Okay, I don't want the full 100-gram batch, I only want 30 grams. Use the formula, tell me how much gentamicin sulfate I would need to provide the right amount of moiety, in this case, just gentamicin. Where would you start with? Let's start with this bad boy right there, right? That's how much we are going to want to make, so that'll determine how much gentamicin we need. So let's just be careful with our units. I want 30 grams of ointment. And since I'm trying to determine how much gentamicin is in there, what I can look back in the formula say that there is 300 milligrams of the base, not the sulfate, but there's 300 milligrams of the base in 100 grams of the ointment. So my first conversion would be to convert from weight of ointment to the weight of just the gentamicin base. Is everyone okay where that came from? Kind of the first step. Clearly the amount of gentamicin will be determined by the amount of ointment I'm making, so start with my 30 grams of ointment, and all I've done is figured, look at the formula. The formula is for the pure gentamicin base, not the sulfate. So now I'm in gentamicin base. Well, how will I convert from there? Well, I'm going to use this information right here to be able to convert, because I know that for every 1 milligram of gentamicin sulfate, it contains 0.59 milligrams of gentamicin base. All right? So by doing it in this way, again, milligrams of the base cancel, and I'm now in milligrams of gentamicin sulfate. All right? That's it. So just do that math all the way across, and you get 153 milligrams of the gentamicin sulfate. All right? Questions with that? Nobody's barking at me. That's good. All right, so let's keep it going. I like this one. This is the definite question right out of chapter, what was it, 20? Speaking of moieties and compounds and all that other stuff. Because it says, how many milligrams of beta-methazone valerate with a molecular weight of 477 should be used to prepare 30 grams of this ointment? Keep in mind, if you look at the formula, it wasn't listed as beta-methazone valerate, it was for the pure moiety, just beta-methazone. I wanted 273 milligrams of the beta-methazone moiety per 100 grams. All right? So how many milligrams do I need for 30 grams of this ointment? Where do you start? You start by making sure you know what's what. Okay, in this case, I'm going to label M for moiety equals beta-methazone. I don't want to get confused. C for compound is the compound that contains the beta-methazone. That's the beta-methazone valerate. Right? Very important with these to label what's what before you do any of the math. Because what I'm going to do when I start with my 30 grams of ointment, what am I solving for? What is given in the formula? The moiety or the compound? The moiety. I just want to make sure that when we do this simple math here in a minute, what we're solving for is the amount of moiety called for in the prescription. So I'm going to start with my 30 grams of ointment. And again, I'm going to multiply by the fact that I was told of the moiety. There's 273 for every 100 grams. Okay, so now if I multiply by my weight of ointment, I get milligrams of beta-methazone, which is the moiety. So do that math, and the prescription to do 30 grams, I would need 82 milligrams of just pure beta-methazone. Right? But now I'm trying to convert that to the equivalent weight of beta-methazone valerate. So if you remember, what we do is we set up a ratio of moiety over compound in terms of the molecular weights. We were given the molecular weight of the moiety as 392, so I'll set that over the compound's molecular weight, which was 477. Set that equal to, again, this is my target amount. This is the amount I'm going to have of the moiety. So if I put 82 milligrams on top, because it's the moiety, over X, when I solve for X, it'll be the weight in milligrams of the compound. And you do that math, and you should get 100 milligrams. And that is C, and C was the beta-methazone valerate. Okay? Questions on these? They're pretty straightforward, but they're real easy to get confused between which is what and what was what. So I know you never like to do what I tell you to do, but try to start by writing M equals this, C equals that. That will, if you just kind of write that out, then as you start setting up your numbers there, hopefully you'll keep them in the right order. All right? Now you've seen these before, the same kind of question between calcium carbonate and calcium citrate. I like it because it's just fundamental skills. The next two questions all are about Milliequivalents. And I wouldn't be so worried, but historically we have struggled now on two different exams. Some of you, again, are still kind of trying to get this figured out. So I'm not trying to make these questions hard, but you've got to be able to convert from weight to moles and moles to equivalents, if you will, or millis and all of that. Let's read the question. Patient is taking 2 Osgow tablets, which are calcium carbonate. And each tablet contains 650 milligrams of the calcium carbonate, with the formula given there and a molecular weight of 100.09. How many milliequivalents of calcium is she receiving each day? Okay? How many tablets is she taking? 2. Let's start with that. So I would argue what we're going to start with here is the fact that she's taking 2 of those tablets. That will tell us how much she's getting. Let's start with 2 tablets. She's taking 2 tablets. Let's go from the number of tablets to the weight of the calcium carbonate in those tablets, because we know each tablet contains 650 milligrams. So I'm going to multiply it by 650 milligrams of calcium carbonate per tablet. My tablets cancel. Now I'm in the weight of calcium carbonate. Let's convert, and since I'm in milligrams, I don't have to do this, so we're in milligrams. Let's convert from the weight, milligrams, to the number of molecules, millimoles. What do? We use the formula weight. So remember the formula weight in milligrams for every 1 millimole, that by putting it and multiplying like that and essentially dividing by the value, we cancel milligrams of calcium carbonate, and yay, I'm in millimoles of calcium carbonate. Okay? Let's look at the formula. Look at this formula right here. How many calciums are in 1 molecule of calcium carbonate? 1. Since it's 1, there's a 1 down there, okay? There's 1 calcium ion per every 1 millimole of calcium carbonate. So now I've converted from the number of molecules of calcium carbonate to the number of molecules of calcium. And lastly, to convert to milliequivalents, what is the charge on the molecule? The valence is 2, so there are 2 milliequivalents for every 1 millimole. Millimoles cancel, and I multiply across, and I get milliequivalents. Okay? Any questions about that? I know a lot of you are looking bored because some of you got this. I know you got this, but make sure we do. This next question I think is a little bit tricky. Let's see if you can get the trick on this next part. It's not hard, but let's just see. It says, this patient now wants to switch to using ultra-dense calcium citrate or Citracal. Each tablet contains 950 milligrams of calcium citrate, and I give you the formula and the molecular weight. Therefore, what's an equivalent number of tablets? All right? Equivalent to what? To this. So that's what we want to do. Let me change colors here. We want to provide that amount of calcium, but now with a different product. So I'm going to start with those number of milliequivalents. Show me how many tablets of this product would provide me the same 26 milliequivalents of just pure calcium. So we got to work backwards. No biggie, right? So starting with milliequivalents of calcium, what is the valence on calcium? Is 2, so it's 1 millimole per 2 MEQs. Make sure you realize that's where, oh, well, my pen is not very good. Oh, cover it up. All right, so it's 2 milliequivalents on the bottom, so that cancels. Here's the trick. Did you get this trick? So we're in millimoles of calcium ion. Are you with me on that? So here we're at this point, millimoles. We need to go from millimoles of calcium to millimoles of calcium citrate. How many calcium citrates, or how many calcium ions are there in 1 calcium citrate molecule? Look at the formula. There are 3. Oh, my pen is so inaccurate. I'll never make this right. All right, there it is. Do you see that big old 3 right there in the formula? So that's why there is a 3 down here. There are 3 molecules of calcium for every 1 molecule of calcium citrate. So this is what the hardest part of this question would be on the test, is this part right here. I think you've got the milliequivalence and the valence. That's pretty straightforward. Hopefully you got that down. But don't forget, you've got to go from ion to parent molecule when you're working backwards like this. And in this case, the molecule is more complicated. There are 3 calciums in every 1 calcium citrate. So that's why in 1 millimole of calcium citrate, there are 3 millimoles of calcium. Okay, so that would then cancel out the millimoles. Then simply multiply by the formula weight in milligrams to convert from millimoles to milligrams. And then lastly, that's the total weight to convert to the number of tablets. We said they were 950 milligrams per tablet. So that's where that comes from. 950 is the amount per tablet, so we'll put that there. Multiply by that, so then milligrams cancel, and we would end up in tablets. All right. Questions about that? All right, let's see if you can do it. Now, this one's the same kind of question, just broken up. But if there has been a thorn in some of your sides this semester, it has been calcium chloride. All right, so let's just do this. We had a couple of questions on calcium chloride, so let's see if we can do this. It's pretty straightforward. It says you have 147 milliliters of a 10% weight per volume solution of calcium chloride with the formula there and a molecular weight of 147. Okay? So 147 milliliters of this 10% solution. First question, and then we just broke this question into parts here. This should be easy. Calculate first the millimoles of calcium chloride. What is the number of molecules of the calcium chloride? Okay, where would you start? Well, the amount is the amount in that, so let's start with that. We have 147 milliliters, okay? Then the fact is, what is the concentration? The concentration is a 10% weight per volume. That means 10 grams per 100 milliliters. Multiply it that way so that milliliters cancel, and boom, I have the weight of the calcium chloride in grams. Let's multiply by 1,000 to go from grams to milligrams so that we can then convert to millimoles, which is what the question asked for. And we do that by dividing by the formula weight. So the formula weight for calcium chloride was given to us as 147. So again, milligrams will cancel and we will be in millimoles of calcium chloride. And I would argue that gives you 100 millimoles of calcium chloride when you do that math. Okay? Easy, I hope. Now let's calculate the number of milliequivalents from that amount of calcium. So again, we're still starting with this amount of calcium chloride there. So starting back from there, let's calculate the number of milliequivalents we would get, okay, of calcium. So to do that, let's convert from calcium chloride to calcium. So let's look at the formula. There's 1 Ca for every 1 CaCl2, so 1 calcium ion for every 1 calcium chloride molecule. So calcium chloride converts to calcium ions. And lastly, since the valence is 2, we'll put the valence in front of the milliequivalents. So we'll multiply by 2 MEQs per millimole. Millimoles cancel, get across, and you get 200 milliequivalents of calcium. Okay? Millimoles, milliequivalents, milliosmoles. Remember osmolarity. Milliequivalence is a measure of the valence, the electrical charge. Milliosmol isn't about valence, it's about what? What's the difference? Milliequivalence, charge, milliosmoles, particles, number of particles. We don't care what the charge is, it's about the number of particles. So let's start with the same thing. To calculate the osmolarity, let's start with the total amount of calcium chloride we're starting with, which we said was 100 millimoles. And how many particles are there for every 1 molecule? For 1 molecule of calcium chloride, there would be 1 calcium and 2 chlorides. Calcium plus chloride is 3. So there are 3 particles for every molecule. So let's take 100 times 3 and get 300 milliosmoles. The problem is that was the 300 milliosmoles is the amount per what volume? 147. Remember that. Don't forget that that's the amount in the 147 mils. So you can do this however you want. You can either set a proportion or you multiply by 1,000 mils. If you do that, then again, you'll get the number of milliosmoles if you had 1,000 mils, and that would be 2,040.8 milliosmoles per liter per 1,000 mils. And that would be your osmolarity. Okay? Questions about that? You guys have done really well with osmolarity. That's the last trick of making sure you proportion it out. You could have done a proportion. You could have done 300 over 147 equals X over 1,000. However you want to do it, it's the same thing. But make sure you do get your final value per liter if you're doing osmolarity. All right? Ooh, let's dilute something. Are you ready to dilute? All right, so let's dilute some boric acid. So it says how many milliliters of a 1 to 50 weight per volume concentration of boric acid solution can be prepared from 500 milliliters of a 4% weight per volume solution. Okay? This sounds like a C and a Q and a mass thing, if you remember. When we dilute something, does mass change? No, so the mass before equals the mass after. Let's just set some of that up. So what are we starting with? We are starting with, the question wants to know how many milliliters, so I don't know. So my first quantity 1 is X milliliters of a 1 to 50 solution. That's what I'm starting with. Some volume, X milliliters of a 1 to 50 concentration. What I use to get, what I get at the end, my 2's, would be a 4% concentration, okay, and 500 milliliters, okay? So again, you get 500 milliliters of a 4% solution and get some volume of a 1 to 50 concentration. So the problem here is, we have to be in the same units. Does milliliters match? Yes. Does that match there? No, that's a problem. So let's go ahead and figure out what to do with that. So let's change the 1 to 50 to a percent. Well, we got to get the same units there. So if I do 1 to 50, that just means, I'm just rewriting it, 1 to 50 means 1 gram per 50 milliliters, okay? Well, we want a percent is a per 100 milliliters, so if we just multiply the top and the bottom by 2, that would give me 2 grams over 100 mils. That's by definition 2%, okay? So I would argue a 1 to 50 is the same as a 2%, so I can take 2% and replace that back up to here. So now if we want to look at our masses, mass 1 would be my 2% times X milliliters. And we said that's going to essentially equal, what I get in the end is 4% times the 500 milliliters, right? So let's just do that math. 2 times X is 2X, and we said that's equal to 4 times 500, which is 2,000. So 2X equals 2,000, divide each side by 2, and X equals 1,000 milliliters. And remember, look back above, what did we say X equals? X equals the volume, in milliliters, of the 1 to 50 concentration solution. So 1,000 milliliters is the answer to that question. All right, I like this one. This is kind of a cool question. Not hard, but it's a little more clinically relevant to some extent. You do this a lot in the hospital when people come in, they're taking oral medications, and either there's a problem with the GI tract, or some other reason we want to switch them to IV. So here we got a patient who's been taking Armour thyroid, okay, thyroid medicine, 2 grains daily. And you can see on the picture down there, they come in 2-grain tablets. So he's been taking 1 2-grain tablet every day. For whatever reason now, he's unable to take this by mouth. He's in a hospital, so we want to be able to convert him over to an equivalent injection, but they don't make an injectable for Armour thyroid. They make an injection for an active ingredient in the Armour thyroid, which is the levothyroxine. So what we want to do is convert from oral thyroid to IV levothyroxine. So to do that, there's some really important things you got to know here, okay? First of all, we're going to say that 1 grain of the thyroid medicine is equivalent to 100 micrograms of levothyroxine. Okay, and you can kind of see on that, it's not exact, but on the bottle there you can see there's a certain amount of levothyroxine within Armour thyroid. We're saying there's 100 micrograms per grain of the Armour thyroid. Again, we're going from an oral route to an IV route. So remember when we did some of our pharmacokinetics, we talked about bioavailability and not a complete absorption. So we're going to say that levothyroxine is only 75% absorbed from the GI tract. So not all of the dose he's taking orally is getting into his blood. In fact, only 75% is getting absorbed. So we're going to have to account for that. And then lastly, we're going to have to convert whatever amount of levothyroxine he needs to the volume of the injectable. So we need a concentration, and the concentration is 200 micrograms per 5 milliliters. And the question is, what volume? Tell me how much injectable. Well, clearly it's going to start with the amount of thyroid. What did we say he's taking? How much per day is he taking? 2 grams daily. So let's start with that. So I'm going to use some abbreviations. I'm going to use capital T for thyroid. So he's taking 2 grains, not grams, be careful, it's grains of thyroid. Okay, that's what he's starting with. We were then given this conversion, the fact that 1 grain is equivalent to 100 micrograms of levothyroxine. So let's use that factoid to convert from T, which is thyroid, to L, which is levothyroxine. So if we multiply by 100 micrograms of levothyroxine per 1 grain of thyroid, then grains of thyroid will cancel, and I will be in micrograms of levothyroxine. Okay? That's the amount of levothyroxine he's been getting in his pill, swallowed every day. All right? So I not so much cared about how much he's swallowing. What I want to know is how much is getting into his blood. So the second factoid we can use is this one here, that 75% of any dose swallowed will be absorbed. So how could you express that? That basically means that 75% is 75 out of 100, meaning 75 micrograms actually is absorbed when he swallows 100 micrograms. Okay, 75% absorption, 75% gets in out of the 100 he swallowed. So now when I multiply it this way, micrograms of levothyroxine swallowed cancel, and we're now in micrograms actually absorbed into the blood. Well, that's where we're going to be injecting our drug, so that's the amount we want to replace. Let's just convert that amount, that weight in micrograms, to the volume of the injectable. We were given the concentration right here. There's the concentration of the injectable. So let's use that, set it up so that micrograms cancel, and our final units would be in milliliters. And if I multiply that across like that, I would get 3.75 milliliters. That provides the right amount of levothyroxine. So it's interesting. This was an interesting question. There are a lot of things to have to take into account. The actual amount of active ingredient in the original product, the bioavailability of the product, and then the concentration of the solution we're actually going to use to inject. Okay. All right, let's keep going with some IV problems. We got one where a patient needs to receive 2 milligrams of bupivacaine per day via an intrathecal pump. As a reminder, I put that picture in there so you can remember where your intrathecal is. Try to touch your intrathecal. It's in your spinal column. It's going directly into the spinal column, into the CSF. So it's a way to put a drug essentially directly into the brain, bypassing everything else. So we want this pump. We got this silver canister where if you keep reading the question, it says that canister essentially holds 50 milliliters. So we can have 50 milliliters of solution in there, and that the concentration of the solution in that pump is 0.25%. 0.25 grams of bupivacaine per 100 milliliters in terms of concentration. And the question actually says, first of all, what should the infusion rate in milliliters per hour be for this pump? The rate. Well, the rate will be the amount we need to get the right amount of drug. And what we want is 2 milligrams per day. Would you agree? We're going to pump it in, so at a rate that gives us 2 milligrams per day. Because I know a lot of you are always, how do I start that question? Or how do we start these questions? The rate will be dependent on the amount of drug the person needs. The person needs 2 milligrams per day. So I set that up as a proportion. Now I just need to convert units. Instead of milligrams per day, I need to get milliliters per hour. All right. So the first thing I did was just to convert units from grams to milligrams. You'll see why here in a minute. So basically I divide by 1,000 so that I can convert milligrams to grams. Now I'm in grams per day. And I can use my concentration because here I was told it's a 0.25%. That's 0.25 grams per 100 mils. If I set it up like this, then grams cancel, and I have my volume per day. Okay? I'm in milliliters per day, but I want in milliliters per hour, so the last thing I'll do is convert by multiplying by 1 day. There's 24 hours, so that my days cancel, and my final remaining units would be milliliters per hour. If you do that math across, you would get 0.03 milliliters per hour. All right. How many days will this infusion last? Interesting. Okay, we know the rate it's going in at 0.03 milliliters per hour. How long will it last? Well, wouldn't it determine the rate? Wouldn't the faster it get pumped out, the shorter the time would be, right? But in the end, we'll start with what? With how much did we start with? How long it will last will depend on how much fluid we started with. And we're starting with 50 milliliters. So let's start this question with the fact that, okay, it will last. I've got 50 mils. It will last until I pump it all out. So what is the rate I'm pumping it out at? I'm pumping it out at 0.03 milliliters per hour. I set it up like this so that milliliters cancel, and boom, there's your answer in hours. But we did want it in what? Days. So the last step is simply converted from hours to days by multiplying the fact in 1 day there's 24 hours. So that hours cancel. And if you do that math across there, you get 69.4 days. All right. There are definitely some questions, or a question I know. There's the section of the chapter on IV solutions and so forth. When we talked about dosing, these can go under dosing, IV infusions. But let's take this a little bit further. Well, okay, no, we'll do that in a separate question. Let's go. Last one here, and we'll probably run out of time. This is a good one that's a little bit difficult. We'll do 2 versions of this. It's about the dilution and altering product strength. The pharmacist has mixed 50 milligrams of an experimental drug with 334.5 milligrams of lactose. 50 milligrams of drug, 334.5 milligrams of lactose. Mix them together, okay? However, whatever that concentration is not right because we want a 1 to 10 weight per weight concentration. Obviously, it's more concentrated than what we want, which is 1 to 10. So how many additional grams of lactose do we need to add to lower the concentration down to the desired? The reason that this question is hard on its surface is I didn't give you anything uniform. I didn't even tell you the concentration initially. And then the desired concentration I gave you as a ratio strength. So let's fix that. The first thing I would do is let's get everything into a percent. Tell me what is the percent concentration of my drug to begin with, and what is the percent concentration I'm trying to get it to. Then I can see what I need to do. So this could be kind of tricky for some of you. Just a little bit of a trick here is let's determine the percent concentration of the initial mixture. The initial mixture has 2 things. It has this and it has that. All right? So what we need to know is our active drug in the total weight. Well, I need to determine the total weight. And I've done this in grams. Don't freak anyone out. I've converted those numbers to grams. So would you agree that my total weight is my drug, 0.05 grams, plus my lactose, 0.3345 grams. Add those together. Here's my total weight, okay? And there's my total amount of drug, if you think about drug for experiment. So my percent concentration is going to be drug over total weight, right? You just divide it out, but that's not a percent. A percent is the amount per 100. So I just used that proportion and said, okay, I've got 50 milligrams or 0.05 grams of drug over a total weight of 0.3845 grams. Okay, set that equal to some X grams over 100 grams. You can do that however you want, but this just proportions that same proportion out to 100 grams, and the answer X there is 13, so that means 13%. I think I did that kind of fast or weird for some of you, but are you okay with how to do that? All I've done here is determine if I have 50 milligrams and I add it to 334.5 milligrams, mix it together, that overall concentration expressed as a percent is 13%. Okay? Now, what did the prescription call for? It called for a desired of 1 to 10. All right? So 1 to 10, weight per weight is 1 gram per 10 grams. If you just multiply the top and the bottom by 10, that would be 10 grams per 100 grams, which is 10%. So this is what I have. This is what I want. Would you agree? Those two need to come together. So I need to go from 13% down to 10% by adding lactose, which has what strength? 0%, right? There's no drug in lactose. So this is essentially a mass 1 plus mass 2 equals mass 3, if you will. So let's just set up our C's and our Q's here. What we said we started with here is we started with 13%, okay? And we know how much of that we started with. We started with 0.3845 grams. So clearly the mass of what we're starting with is 13% times that weight, okay? What are we adding to that? We're adding to it some unknown amount of lactose. So the unknown amount is X grams of lactose. What is the concentration of lactose? 0. What is 0 times X? 0. We are not adding any additional drug. That's why the mass is not changing of the drug. So 0 times X is 0X. But what will we get in the end? What we want in the end is my 10%. So that's what I want in the end. And this is the trick. Make sure you can do this. Remember, the quantity is just going to be the sum of the two products. I start with 0.3845 grams of my initial mixture. I'm adding X grams of lactose. My final quantity will be 0.3845 plus X. Okay? So let's just set those two masses equal to each other, since again, adding the lactose doesn't change the mass, so I can say that 13% times 0.3845 is equal to 10% times 0.3845 plus X. Do the math carefully. You get 5 equals. Remember to carry the 10% into both parts. 3.845 plus 10X. Subtract the 3.845, you get 1.155 equals 10X. Divide both sides by 10, and X equals 0.1155 grams. On the Aliquot review, I was just emphasizing here that there are 2 acceptable answers. Certainly on the test, either answer would be okay in terms of the amount of lactose. Either my way with the 240 milligrams, or I think being more traditional with the way Dr. Dukoski said, would be 225. I want you to realize the only difference is if you subtract the drug weight here, then you weigh the aliquot amount of the mixture. If you did it the way I did it and subtract the aliquot, then you weigh out the drug amount of mixture. So it's just reversing those 2 numbers there in terms of the way you make it. And so there's no right and there's no wrong. And I should have been more consistent with the way he does it. The way that I learned it and the way he used to taught it was to use the least amount, essentially, of drug. So instead of using the larger amount of drug, I chose to use the smaller amount of drug, which makes the amount of aliquot mixture a little bit higher. But it's the same either way that you do it. So if you have any questions about that, please ask me. I'm not trying to make anything confused. I just want you to realize that if you did it kind of the other way, the way Dr. Dukoski said, with that one little difference between where you weighed out what, it's completely acceptable. On the exam, I certainly would accept both answers because they're both right. The other thing that I sent an email about was my little typo here for this question here was for the cocaine. I had 0.6% listed here, and it should have been 60% like it is here. So again, on the previous slides, this is a little bit different. The answer is still the same because I had intended it to be 1.5 milliliters. So the answer was the same, but I had typoed the concentration wrong for that cocaine. It should have been 60%. So anyways, but otherwise everything else worked the same there. Okay? So beyond that, let's get back to where I left off here. So we had just kind of done a dilution question that was going to be about to be worked both directions. So we had finished off on 8A, and now, so 8B, I'm going to skip over. It's the same question using an aliquot. I know the answers are on there, but we're going to be, aliquot, I'm so excited, an allegation. So we'll do some other allegations, so I don't want to belabor that point for now. So, oh, wait a minute. Didn't we already do that question? Where'd that one come from? Well, since it's here, maybe we should work through it anyways, only in the sense that I do believe there was a bioequivalence question on the final exam on that sheet that I gave out. Since this slide is here anyways by accident, let's just answer it to make sure that you know how to do this question. So we had done this before. Let's just see if it comes back to mind. Bioequivalence means essentially the same amount of drug from two different dosage forms. So the question says, if a drug is 40% bioavailable from the oral route and 58% bioavailable by the transdermal route. Okay, so again, the drug gets into the blood slightly different between those two routes. If in the oral route, the patient is taking 2.5 milligram dose of nitroglycerin twice a day and is going to be switched from that oral form to a transdermal form, and again, the transdermal form is a 2% ointment, well, how much of that ointment would they need to get the same amount of nitroglycerin where? In the blood, okay? In the end, we want to get the same amount from two different routes, all right? So the first thing I would say, well, let's clarify how much dose they're getting from the oral route, because 2.5 milligrams twice a day doesn't tell me the total daily amount. So let's take the 2.5 milligrams times 2, so that I know per day they're actually taking 5 milligrams of drug by mouth every day. That's the dose, okay? Does all 5 milligrams end up in the blood? No. So what we're going to try to do, and the whole point of bioequivalence says, is you take the fraction that's absorbed and actually gets into the blood times the dose, right? So again, if it's 40% bioavailable, then only 40% of the 5 milligrams is going to make it. That's the dose that we want to be the same as if we had applied it through the skin in this question. So let's take its fraction times the dose and set it equal to the fraction times the dose from the transdermal system. All right, so let's put in some values for the F's and doses, if you will. On the left-hand side for the oral, if you look in the question, it said it's 40% bioavailable. That means the fraction is 0.4. That's 40%, same number. So let's put 0.4 times, we just said the total daily dose was 5 milligrams. So 0.4 or 40% of 5 milligrams. Let's set that equal to whatever the fraction is from the transdermal, which we say is 58% or 0.58, right, times what dose? We don't know. That's what we're solving for. We want to know how much dose to put transdermally to be the same as the oral. So let's solve for x. Pretty simple math at that point. 0.4 times 5 is 2, and that equals 0.58x. Divide each side by 0.58, and essentially we need to use a 3.44 milligram dose of nitroglycerin topically or transdermally. That would be the same as the amount that we're getting from our normal dose by the 2 capsules. All right. The last part of this question says, okay, but we want it from the cream, and the cream, or the ointment in this case, is a 2% concentration. So how much of that actual cream provides the 3.44 milligrams? So I started with the 3.44 milligrams, and let's just convert from milligrams to grams by dividing by 1,000. That's all I did there. Now I'm in grams of that dose, and again, a 2% weight per volume means what? 2 grams of nitroglycerin per 100 grams of ointment. So if we multiply it so that the grams of nitroglycerin cancel and we end up with grams of ointment, you multiply that across, and that's where the 0.17 grams of ointment would provide the same, or essentially provides the 3.44 milligrams of nitroglycerin, which is the same as taking 2 2.5 milligram doses. Questions on that? That's what we mean by bioequivalence, and those are the kinds of questions that you could expect for that. All right? All right, well, let's keep going on with some of the other general review questions, and some of these I hope are kind of easy. This is a fun one. It says the dose of the mitomycin is not fun. It's a chemotherapy drug, so not a good drug, but a dose for mitomycin for a patient who needs it is 20 milligrams per M2. What the hell is M2? Is that a weight? M2, meters squared. That's not a measure of weight. That's a measure of what? Body surface area. It's an area. So again, it's 20 milligrams per meter squared, which is a measure of body surface area. Therefore, we need to determine the dose for this patient who weighs 144 pounds and stands 68 inches tall. Well, what do we need to do to get to meter squared? We need to determine her body surface area. okay, or the patient's body surface area. And there was a formula for doing that. The formula, though, requires the height to be expressed in centimeters and the weight to be given in kilograms. So let's first convert the values we were given to those units so that we can then use the formula, okay? So 140, well, I'll start with the height. So 68 inches in height, multiply by the conversion factor of 2.54 centimeters per inch. Inches cancel, and you get 173 centimeters. Do the same thing for pounds, and again, hopefully this is pretty straightforward. You take the 144 pounds times 1 kilogram over 2.2 pounds, pounds cancel, and you get 65.5 kilograms, all right? I will tell you on the exam, again, you can have your note card. You can certainly write some of these things out. It's not unreasonable for me to provide you those conversions. This isn't necessarily an exam to memorize conversion units. Just make sure you use them correctly, because what could possibly go wrong if you look at those two conversions? It turns out you multiply the height by 2.54, but what do you do with the weight? You divide by 2.2. So a very common mistake. I know these are easy calculations. I'm just warning you as you set it up. I know y'all don't like to do this, but if you cancel your units or double check, then make sure you put the number in the right spot. It is easy to make a mistake. And there was a high strength. You guys, have you talked to the P2s yet? They have this OSCE that they have to do, this high stakes OSCE you do in your second year. And part of it is calculating a dose. And I had to remediate a couple of students who failed part of it because they multiplied by 2.2 instead of dividing by 2.2. That significantly changes the overall dose. So it wasn't that they didn't understand, they made a mistake. And again, that's just saying is that as you do these math things, not to make simple mistakes, is just to take your time and watch your units. All right, having said that, the most stellar formula for body surface area that we were given was simply to take the height in centimeters times the weight in kilograms, divided by 3,600, and then don't forget to do the what? The square root. So take the square root of that. So I show you my work there. If I do that math, essentially you get 1.77 meters squared. All right? Well, what was the point of doing the body surface area? So we could calculate the dose. So let's take their body surface area, 1.77 meters squared, times 20 milligrams per meter squared, and clearly meters squared will cancel, and we'll get our dose in milligrams, and that's where the 35.4 milligrams per day comes from. Okay? And there are definitely some dosing questions on the test. I mean, you don't always have to ask hard questions. A good pharmacist is somebody who can do easy calculations, but do them without mistakes. And that's what I'm just saying, double check yourself. This is another good example of a question I don't think is difficult, so long as you know where to start and convert your units as you go across. It reads that a patient with a body surface area of 1.5 meters squared, so I've already calculated that for you, is to receive 7.5 milligrams per meter squared per hour of cytarabine. How many drops per minute, again, this is kind of, okay, drop per minute, so it's an infusion rate issue, of an IV infusion containing a concentration of cytarabine of 100 milligrams per liter should be given if the infusion set delivers 20 drops per milliliter. This is just a question of information overload. There's a lot of things there, a lot of conversions to do. We have to be careful with our units, okay? So let's just do one step at a time. Clearly the dose, 7.5 milligrams per meter squared per hour, is going to depend on their total body surface area. So let's start with this. This is where you would start that question, and then we can work all the way across from there. All right? So I started with my 1.5 meters squared. Then multiplied times the dosing, which is 7.5 milligrams, and this is where I'll still emphasize this. Try to write it in that format. It makes it easier to see, because if I write it that way, then I can see that my metered squared cancel, and my units now are in milligrams per hour, okay? So you can do a couple of things. Let's save the time for now. We don't want milligrams. We need essentially drops. We want to know drops per minute. So we got to convert milligrams to drops. So let's first convert milligrams essentially to a volume, because I'm given the concentration. Here's my concentration, if you will, of cytarabine. It was 100 milligrams per liter. So if I multiply it by 1 liter over 100 milligrams, then milligrams cancel, and I have a volume. Now, it's a stupid volume. It's in liters. That's not particularly helpful, but we can fix that. Let's convert it from liters to milliliters by multiplying by 1,000 mils on top per 1 liter. Now I've got milliliters per hour, but I want drops. Okay, so let's look at the drop factor, and that was given to us at 20 drops per mil. So if we multiply it in that fashion, then milliliters will cancel, and I will be in drops, and I'm done. Almost. I'm in drops per what, though, at this point? What hasn't else canceled? Hour. So let's not forget about time. It wanted our final answer to be how many drops per minute. So our last step would be to multiply by 1 hour over 60 minutes, so that hours cancel from way over here. And you'll notice the last remaining units are drops in minute. If you do that math going across, you get the 37.5, which you would clearly round. Any questions on that? Again, a lot of separate conversions, and that's the only trick to any of those infusion questions will just be to take your time to do that. All right, I like this question because it's about as a tricky way to express a dilution as possible. Tricky in the sense that reading it, it's a little more difficult to figure out what's the C and what's the Q part to the C and Q thing. So let's see. It says, how many milligrams of sodium fluoride are needed to prepare 100 milliliters of a sodium fluoride stock solution? All right, so do we know the concentration of that solution? No, it wants to know how many milligrams per 100 mils. So what it's essentially asking for, even at this point, is a concentration. You don't know the concentration. You want to know how many milligrams per 100 mils. You want to kind of know what the concentration is. Okay, but you want the concentration such that what? Such that a solution that contains 2 parts per million of sodium fluoride results when 0.5 mils of the stock solution is diluted to 250 mils of water. Okay, that is a convoluted sentence. What you need to do is mark what goes with what. All right, so let me circle this. Here's 2 parts per million. Would you agree that that is a concentration? That is a concentration. Expressed in parts per million, but that's a concentration. What quantity, in this case volume, what volume goes with that concentration? We get that concentration with a total final volume of 250 milliliters. So that goes to the Q, and these two go together. Okay, there's the C and the Q. All right, so what is this 0.5? That's the quantity, if you will, of the solution that has a concentration that we don't know. Okay? So, do you see where I could have rewritten that question and re-expressed that in different ways? It was written in a way for maximum confusion, that the information was given to you in a way that you had to really piece it back together. So instead of looking at my scribbles here, did you or could you come up with the right C's and Q's? The math is easy, but we're saying that the first concentration we don't know. We want to know how many milligrams to add to 100 mils, so we don't know the concentration. So I set X equal to my concentration, and I say X percent. That's the percentage concentration of the initial solution. I don't know what it is. But I know how much of that solution am I going to use in my final dilution. It said I'm going to use 0.5 milliliters. So my Q for that quantity, for that concentration, my Q is 0.5 milliliters. I'm going to take half a mil of whatever that concentration is. And what am I going to do with that half a mil? I'm going to dilute it up to a total volume of 250 mils. So my Q2 is the 250 mils. I know what my final volume is going to be. And I was told that that final concentration is 2 parts per million. So my C2 is 2 parts per million. Any questions about that? I would argue once you know that, the rest of this is very similar to what we've done in the past, okay? So I'm not going to say all the questions are going to be intentionally written this way, but this is a good review question because it did make a not difficult calculation as hard as it could be just in terms of being able to set it up initially. So at this point, the biggest issue at this is still, this ain't going to cut it. I don't want parts per million. I want it in a percent. So what I did down here was simply convert 2 parts per million. I said that means 2 grams per 1,000,000 milliliters. That's 2 parts per million. Set that equal to X over 100 mils, or essentially determine how many grams would be equivalent at 100 mils. And essentially it is 0.0002. So it's a tiny number, but it's okay. I can deal with it. So that number, essentially expressed there as a percent, because it's per 100 mils, is what I'm going to substitute here. So you'll notice that's what I put over here for my mass. Okay? So essentially now I can essentially say this is a dilution. So the mass I had before is equal to the mass I had afterwards. So my X percent times 0.5 mils is going to be equal to what I just determined to be 0.0002% times 250 mils. The mass isn't going to change between those two. Solve for X, you can see the math there, and my final X, though be careful, my value is 0.1. That represents 0.1%. That's what I said X was equal to, was a percent concentration. That's not the final answer to the question. That is the concentration of the solution I have to have. That's the concentration of that stock solution. But it wanted to know what? How many milligrams per 100 mils. So the last step is, okay, if I have 100 milliliters, let's multiply it by that concentration, which we said was 0.1% or 0.1 grams per 100 milliliters. If I multiply 100 mils times that, that would tell me how many grams. And lastly, let's multiply by 1,000 to convert that to milligrams. And that would be, final answer would be 100 milligrams. If I put 100 milligrams into 100 milliliters, that's a 0.1% solution. If I take half a mil of that and dilute it to 250 mils, it gives me 2 parts per million. Questions on that? Yeah, please.
I was just wondering if you have any tips. Like, I had tried this one, and I thought that the 100 milliliters was like another Q value. So like, I thought that there were 3, which actually like gave me like the wrong answer.
Right.
So I was just wondering like if you had any tips on like differentiating that.
Yeah, the biggest tip I would have, so let me go back, is looking through this, and let me erase all this stuff. The tips are, before you just automatically put numbers down for stuff, is to, let's see, let me erase all of this garbage. For here, is how to answer that question. Is I would start at the end. What I would try to do, because you need some sort of concentration to use some amount to end up with something. So I would start at the end. What is the final solution it says that you get? What is the result? So if I look at here where the word says results, the result is a solution that has this volume. Does that make sense? Do you see where I said 0.5 milliliters there? And it comes after the word results, but it doesn't make sense. It's when you use that amount to get something else. So that's not right. It says such that a solution containing that concentration is what results. Does that make sense? So what I was trying to show you here is try to draw those two together. Start at the end. What I get at the end, what you see now working back here, is that, did it make sense that your final concentration was 2 parts per million? Okay, and did you associate it with the 250 mils? Okay, so that's good. That's what you get. So then ask yourselves, how did I make it? And remember, when they say, how did I make it, there's only 2 things. You need a concentration and you need a volume. And you may not know any part of those, but you have to have one or the other. Does that make sense? To solve it, you need one or the other. So in this case, it did very clearly say that I'm going to use that volume. Okay? So then what's missing is a what? A concentration. So that's where maybe you could ask yourself, what does the 100 mils represent? It says to prepare 100 mils of a stock solution. I don't know. That's the best I could maybe tell you from now. I'm not intentionally going to write the test questions that hard. I don't think that is the point. But this was a good challenging one here to kind of make sure you understand what's a C and what's a Q and how to set that up. So I'm glad I stumped you a little bit. But looking back on this, hopefully you can kind of maybe see how to do all that. Okay? Thank you for asking. Good. All right. That was painful, so let's do a morphine question. It says, an epidural dose of morphine sulfate should not exceed 10 milligrams per 24 hours. Total daily dose, 10 milligrams. You need to set up a patient controlled or a PCA infusion such that the patient can hit that button every 30 minutes, okay? If we didn't pull a lockout, what would they do with that button? Boom, 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 boom. Okay, they just feel the love, right? So no, you can hit it all you want, but it's only going to administer a dose. How often? Every 30 minutes. So they'll only get a dose every 30 minutes. What's the total amount they can get in a day? What dose? 10 milligrams, okay? So that's just from that first part, trying to understand those questions. It says, if you use a solution whose concentration is 0.5 milligrams per milliliter, what is the maximum volume that could be administered per dose, not to exceed the total daily maximum? Again, that's just kind of a confusing question. What are they asking? They want to know, every time I hit the button, what volume of fluid will go in. Okay, how much volume is going to come in every time I hit the button? So let's rethink through some of this, how to get there. What's the total daily dose? 10 milligrams. I cannot get more than 10 milligrams because the fluid, the volume I get in a day is going to be the volume that gives me the dose. The only reason I'm getting the volume is to get the amount of morphine. So we got to relate it back to the dose. The total daily dose is 10 milligrams. Here's a question. How many total doses will they get in a day? If the person hits the button all day long and gets them every time they could get it, what's the total number they could do? Well, they said every 30 minutes. Let's convert every 30 minutes into a number of doses. To do that, I started with 24 hours in a day, right? We wanted to know the amount per day. So if I started with 24 hours and then convert that to minutes, so multiply that by 60, then my hours cancel and I got 60. This is, again, that would give me the total amount of minutes in a day, right? Now, I do know I get 1 dose every 30 minutes. So if I multiply that by that, minutes cancel, and essentially I've just calculated that, and it should hopefully make sense that you get 48 doses if you can get 2 doses per hour. okay, every 30 minutes. So 10 milligrams per day in a total spread out of 48 doses. All right, so let's set that proportion up. This is in the end how to answer this question is really you need to start with that and say, okay, I'm going to be getting 10 milligrams in a day out of 48 doses. All right? The question then wanted to know the volume per dose. So instead of in milligrams, I want milliliters. So how can I convert from the weight of my morphine to the volume? The concentration. That's where the concentration comes from. So I can use that conversion over here, to essentially multiply by 1 mil over every 0.5 milligrams so that milligrams cancel. You then, if you do the math, 10 divided by 48 times 0.5 there, you get 0.42 milliliters per dose. That would be milliliters per dose. Okay? And again, I realize that the trick to these questions is kind of knowing how to start with this 1, this 2, and then finally 3. And the trick essentially is knowing the units to some extent and what are you trying to get to. Okay? So, all right. The second part of that question is an easy one. It says, how long will a 50 milliliter cassette last? All right. Well, it has we have that same concentration. We know how we're dosing it, so we know the total daily dose is that if the total volume is 50 milliliters, let's convert that volume to the total amount of drug in there. How much morphine is in a 50 milliliter cassette? Well, it depends on the concentration. We have that concentration, so 50 milliliters times that concentration would tell us how many milligrams they have, right? How many are they getting? What is their total daily amount per day? 10 milligrams per day. So if I multiply that by the fact in 1 day, the maximum amount they can get is 10 milligrams, then if I multiply that out, then a 50 milliliter cassette would last 2.5 days. So just start with the volume, convert now volume back to the amount of milligram, and essentially just divide by the fact that they're getting 10 milligrams a day. And that's how you can get your days. All right? Let's swing back to some isotonicity calculations as a review. So in this question it says you need to prepare a sterile isotonic solution of a new ophthalmic drug for a clinical trial to treat glaucoma. You need to prepare a 1.5% weight per volume solution of this drug. Now here I give you its molecular weight and its I value. What did I stand for? Not I love calculations. That was a different one. This was the dissociation factor. It has to do with how many particles come out in solution. So don't care about that, but you'll see it here in a minute. We'll use that in a minute. So the dissociation factor was 1.8. The solution also contains 0.4% of chlorbutanol, which is a preservative. And you're going to add some boric acid to adjust tonicity. All right. So the first question is, I gave you the E value for chlorbutanol. Did I give you an E value for the new experimental drug? No. Can you actually calculate an E value if it's not given to you? Yes, you can. So that's the first part of this question, was to use this formula. And again, this is not a formula I would have expected you to memorize. It would be one if provided to you, though, you could be remembered to be able to get the correct E value. So it's simply the molecular weight of sodium chloride divided by its dissociation factor times the inverse for the new drug. So all we got to do is plug in the values we were given. And so for our new drug, the I value is 1.8 and its molecular weight was 278. So if you do that math, pretty simply you could hopefully come up with the E value for this drug, this experimental drug, is 0.21. Okay? So vaguely remember doing all that. I would still say, certainly for my test, I think it's much more important to be able to use the E value than to be able to determine it, but that's where it comes from. It's a number that you can calculate with a fairly straightforward formula, and that tells you what? 0.21 what? This is the trick to this question, or you got to do the E value. If I say E value is 0.21, that means 0.21 grams of sodium chloride per gram of this experimental drug. So just remember, for me on the test, it is be able to use the E values. And we'll do that here in a minute. And to do that, essentially, you've got to answer this next question. It says, how much drug, and actually chlorbutanol, will be needed to prepare 250 mils? So if we're going to make a larger batch of this I solution, we want to make a big batch of 250 mils, to get to the boric acid, we need to know actually how much drug is in there. So that's just a percent concentration. So let's just take the drug. Remember, we're making a 250 mil batch times its concentration is 1.5% weight per volume, 1.5 grams per 100 mils. Mils cancel. Boom. That's the weight of my drug. To make 250 mils, I would need 3.75 grams. Same thing for the chlorbutanol. Its concentration was 0.4 though, so 0.4 grams per 100 mils times our 250 mils gives me the weight of chlorbutanol. So I need 3.75 grams of my drug and 1 gram of chlorbutanol. Why do I need to know the weight of the drugs actually in the solution? So I can determine how much sodium chloride they will mimic in terms of isotonicity, because the next question says, all right, use these E values and use boric acid to determine how much boric acid you need to make the final solution isotonic, all right? Well, like I said, the amount of sodium chloride will depend on the amount of drug. So that's why we had to first determine for our drug, we have 3.75 grams. We just did that. It's multiplied by its E value, which we determined in the first question to be 0.21. And remember, it's 0.21 grams of sodium chloride per gram of drug. So when I multiply now, grams of drug cancel, and I get grams of sodium chloride. So my 3.75 grams of drug mimics osmotically 0.79 grams of sodium chloride. Do the same thing for the chlorbutanol. I won't belabor that, but 1 gram times its E value, which was 0.24, and we were given that, means 0.24 grams of sodium chloride from chlorbutanol. So I know how much I'm getting for my drugs. How much do I need total? What's the target? Remember, you do need to know that an isotonic solution is 0.9%. So let's take 250 milliliters, which is our batch size, times 0.9%, which means 0.9 grams per 100 mils. That would tell me how much sodium chloride I would need total for that volume. So for 250 mils, I need to have 2.25 grams of sodium chloride. Well, I'm getting some of that from my drug, so let's take the 2.25, subtract the amount from the experimental drug, 0.79 grams, subtract the amount from the chlorbutanol, which is the 0.24 grams, and what I still need to get is the 1.2 grams. Where am I going to get that from? The question said to use what? Boric acid. Could you just weigh out that amount of sodium chloride? Sure, if that was the question, you could have just done that, but the question said, no, you're not using sodium chloride. Make up the difference with boric acid. Well, that's okay because I have the E value for boric acid, so I know 0.52 grams of sodium chloride is equivalent to 1 gram of boric acid, so I can just set that equal to my 1.22 target amount of sodium chloride over X. X would be the grams of boric acid to provide the right amount of equivalent sodium chloride. So solve for X and I get 2.35 grams of boric acid. So this was kind of a classic isotonicity question, kind of walking you through step by step as making it as hard as it could be, meaning you had to initially start with calculating the E value, which I doubt I would make you do, but the rest of this is kind of the process for doing these kind of isotonicity calculations with the sodium chloride equivalent method. All right? All right, let's get manly here and talk about some testosterone gel. I could use some. So this question is about altering product strength. So it says how many grams of gel base should be added to 30 grams of the commercial product, which has a concentration of 1.62% testosterone, to decrease its strength to 0.75%. All right? I like this, and you'll see the next question is the opposite. These are the altering product strength chapter. This is about whether you're basically diluting a product or fortifying. In this question, are we diluting or are we fortifying? We're diluting. We're making the concentration lower. We want to go from a 1.62% down to a 0.75%. So do we need to add drug? No, we're not adding drug. We're adding base to dilute it. All right? So could you answer this two different ways? Could you do it by allegation or by the algebra way? Yes, you can do it either way. On the test, since if you think about ExamSoft, you just give me the final answer, right? Do I know how the hell you solve those? No, so do whichever way you want. I will tell you now, I can't force you to do it one way or the other. As long as it's right, you do it whatever way you want. So I'm going to work with them both ways here. And in the end, you want to practice both ways, that's great. But it doesn't matter as long as you get the right answer. So if I start with the whole allegation idea here, because I kind of like that, it's a visual thing. What I'm going to do is put my high strength concentration, which is a commercial product, the 1.62% on top. Down below that, I put the other ingredient, which is gel base. How much testosterone is in just basic gel base? None. It's a base. There's no drug in there. So that's 0%. All right? So are you okay where I get this is my high strength and this is my other ingredient? It's 0%. Then my target goes in the middle on the right-hand side. So I'm shooting for a total concentration of 0.75%. Use my arrows. Starting with the high strength going down diagonally to the lower right, I cross subtract. So 1.62 minus 0.75 gives me the 0.87 value. And then starting from the 0 going diagonally up to the upper right, take 0.75 minus 0 and you get 0.75. All right? So I'll remind you, this number goes with that. That's the whole idea behind the arrows there. This number goes with that. So that remember to divide by, you have to take those values and divide it by the total of both. So what is 0.75 plus 0.87? 1.62. So the total combined weight of both of those two things goes in the denominator, okay? So the value in the denominator essentially is the value that represents the 0.75, because that's the total combined concentration we want when we mix everything together, all right? In this, once you set that up, and the math is easy to do if you kind of just remember those couple of steps, because now you just got to ask yourself, so what do I know? I know I have 30 grams of something. It's 30 grams of what strength? What do I have to begin with, right? It's 30 grams of the 1.62%. So essentially, that's this thing here, right? So that's the 30 grams I have, and that represents this. So let's set that equal to 30 grams, because I know I have 30 grams of my 1.2%, which is representative of the 0.75 parts. I'm going to put that over x, and if I solve for x, I'm solving for the equivalent of weight now that represents the 1.62 parts, which is the total weight. So 30 times 1.62 divided by 0.75 gives me 64.8 grams. This answer is not my final answer. What is this answer? This answer represents the 1.62 parts. Now what I can do is come down here and say, well, now to actually solve for how much gel base, I know I need 0.87 parts of the gel base over 1.62. I can set that equal to x grams of the gel base over my total weight, which is 64.8. And now solve for x, and you can see the actual amount of the pure base that I need to combine with my 30 grams of 1.62% is 34.8 grams of base. And yes, you can just subtract them. If you just take this weight minus that weight, you get that weight. So I'm not trying to make it harder. I'm just trying to make sure you can know what part goes to what thing. Okay? Let's do it the other way. So if you wanted to do concentrations times quantities, would you agree? What did we start with? We started with 30 grams of an ointment that had that concentration. So that's what I'm starting with. What am I adding to it? I'm adding to it pure gel base. What is the concentration of pure gel base? It has 0% testosterone. There's no drug in there. And how much am I adding? Here's kind of the trick. It's X. I don't know. The question is asking how many grams of that to add. So it's X grams of 0%. What do I want in the end? Remember the third thing, when I add my two things together, I want to get a final concentration of that. And again, this is still the trickiest part. My final quantity, I don't know, but I can predict because it's just what I start with, which is the 30 grams plus the X grams of the gel base. It'll be the combination of both of those. Would you agree in this situation that what is 0 for M2, what is 0% times X? 0. So mass doesn't change. I'm not adding any drug, I'm just adding base. So I can say M1, essentially in this case, actually equals M3. So let's take the 1.62% times the 30 grams and set that equal to the 0.75% times the 30 grams plus X. Do that little bit of algebra and multiply that through, and I won't read all of that through here, but hopefully you could be able to solve for X in this case. And X represents essentially the weight of gel base to add, and it's the same answer as we got above for the allegation. Any questions on that? Now, what would be different? Because here's the next question is not to make the strength lower, but let's start with 1.62% and make it higher. What would we do to make it higher? Well, we have to add something that has testosterone in it. It could be a higher strength gel, or in this case, I said how much just pure testosterone. If we just have pure testosterone powder, how much of that should I add to that same 30 grams of 1.62%? But now I want the concentration to go up to 2.5%. All right? So let's work it the same way, but there's just a little bit of variations. So now the high strength actually is the testosterone powder we're adding. What concentration is testosterone powder if it's pure testosterone? It's 100%. So we put 100% on top to represent the testosterone powder. Now the lower strength is the gel we're starting with, the 1.62%, and to the right in the middle is our target of 2.5%. Do the same sort of math here, and I won't belabor that point at this point, but you can set up the proportions. But I would try to remind you that the 0.88 parts goes with the 100%, the 97.5 goes with the 1.62, and remember this larger number on the bottom is what goes with the 2.5 in terms of parts. Okay, because now the question is, what do I know? I know I have 30 grams of the original. Where does that go? Does it go on the top or the bottom? It goes on the bottom. It represents the 1.62%, right? That means it represents the 97.5 parts. So let's set that lower one equal to 30 grams over X. Because I know that my 30 grams of initial ointment, or gel in this case, represents the 97.5 parts, because that's the 1.62% concentration we're starting with. Now if I solve for X, I see that the total weight of my combination would be 30.27. So hopefully if you wanted to do it the quick way, you would just say, okay, that's my total. Let's subtract the amount that I'm starting. So obviously I need a total of 0.27 grams of testosterone, right? That's the quick way I know you'll do on the test. But if you want to be thorough, we would go back and say this total represents those number of parts, and those number of parts are the same up here. So that's where that number gets put, is 30.27 on the bottom there. X over that, solve for X, and you get 0.27 grams. Okay? And I won't belabor that whole point, but you can set it up the same way on the bottom there. And I gave those answers to you on the slides. So any questions? This isn't a hallmark of, that's why we showed you both ways of doing it. Again, for the test, make sure you can do either way of those. I mean, as long as you can answer those questions for whether it's concentration or diluting. Diluting, you don't change the mass. Concentrating, fortifying, you change the mass. So make sure it's M1 plus M2 to equal M3 in this case. All right? All right, these are easy. Let's do just a brain recovery activity here. All right, so let's see. These should be no-brainers. So that's the first one. 15 says, how many grams of nystatin would be needed to prepare a batch of 350 tablets if each of those contained 500,000 units of nystatin? Okay, and I tell you that 1 milligram of nystatin contains 4,400 units. All this is going back to the chapter about units of activity. It's just a different way to express concentration and drug amounts, but we can deal with that. So where would we start? We want to know how many grams of nystatin to make this batch of tablets. How many tablets are we making total? That'll determine how much nystatin we need. 350. So let's start with the 350 tablets. The first conversion is we know each tablet is going to contain 500,000 units. So if we multiply 350 tablets times 500,000 units per tablet, then we know how many units. All right? Once we know how many units, we can use the conversion we were given, that 1 milligram is the same as 4,400 units. So now units cancel. The units of units cancel, and we're in milligrams. But lastly, the question did ask for grams. So to get grams, we're going to basically divide by 1,000, so we can convert milligrams to grams. And you do that math across there, and you should get 39.8. Questions on that? I'll still say I like the dimensional analysis thing, because as long as you set your units up right before you do your math, you should hopefully get the right answer. Number 16 says, an elixir containing 40 milligrams of drug in each 5 milliliters. How many grams of the drug would be used to prepare 4,000 milliliters? Okay, we got a volume, 4,000 mils. We got a concentration. All right. The one last trick I would say is, remember the final answer wants it in grams. So let's just simply set that up with my total volume is 4,000 milliliters. The other thing I will warn you about this on the test in general, just in life, concentrations. It's, this case, 40 milligrams per what? Per 5 mils. Could it have been per teaspoonful? What if it was per teaspoonful? How much would that be? 5 milliliters. Could it have been per mil? That would have been per mil. What about per tablespoon? How many milliliters per tablespoon? 15 milliliters. So just be careful with making sure that you do the math right with the concentrations, because it could be any units in the numerator, any numerator in the denominator. Make sure you just set up your units correctly. But this is pretty straightforward. 4,000 times 40 milligrams per 5 mLs. That cancels milliliters. And then lastly, to convert from milligrams to grams, you basically divide by 1,000 and you get hopefully 32 grams. I put this one here. I love that picture, because if you miss that question, you might need a dose of the Dr. Harrison's elixir there. That was a pretty simple question. All right. Let's talk about acids. You love Henderson-Hasselbalch questions. So again, this is not a huge emphasis. There was one part of one of the chapters for this, so let's make sure you can do the math. It isn't so much about the derivation or anything, because it wants to know the pH. What is the pH of a buffer solution? I provided you the molar concentrations here, which is usually the hardest part, but I gave you that the solution has 0.055 molar sodium acetate and 0.01 molar acetic acid. All right, and again, the pKa is 4.76, and it wants to know the pH. pH is the equation. What is the name of the equation for the pH equation? The Henderson-Hasselbalch, all right? So it is different depending on whether you have acids or bases. So a little trick to this question would be to look at the question and say, okay, are we trying to find the pH of an acid buffer solution or a basic buffer solution? Look at the name of the ingredients, because there's either an acid or a base, and then its corresponding salt. And we were told sodium, what's another name for sodium? Salt, right? Sodium acetate and acetic acid. So clearly this is an acidic buffer solution where we have a weak acid, acetic acid, and its corresponding salt, sodium acetate. So all you had to do is make sure you identified which one was which so that you can put the right number in the right place. And since the Henderson-Hasselbalch says to take the log of the salt concentration, molar concentration, divided by the molar concentration of the acid, since I gave you those values already in molar concentration, all you had to do was put the numbers in the right spot, hopefully on the formula, and then do the math right. I'll still warn you, doing logs for some of you are not comfortable with, making sure you can take 0.055 divided by 0.01, hit the log button then, because then your answer is 0.74. The log of that multiple is 0.74. Don't forget to add that to the pKa, so the final pH value would be essentially 5.5. Okay? All right, so this is an interesting one, only in the sense that it's kind of a tricky question. I don't know if you would just know how to, it says a new drug has a E value, a sodium chloride equivalent of 0.23. We've talked about those, you know what that means. So what is the concentration of an isotonic solution? So that's not hard, but what does it mean to be an isotonic solution? I don't know how much of that drug would be isotonic. Do I know how much sodium chloride would be isotonic? How much sodium chloride is isotonic? 0.9%, right? So don't I need the same amount of drug that gives me the same as 0.9% of sodium chloride? That's where to start with this question. Start with the sodium chloride. So just that idea with 0.9% means 0.9 grams per 100 mils. So let's figure out how much drug we would need for 100 mils, because I know how much sodium chloride. How much sodium chloride do I need for 100 mils? 0.9. I was given the E value. What does the E value mean? 0.23 what? Grams of sodium chloride per gram of that drug. Set that equal to our target sodium chloride, which we just said we needed for 100 mils to be 0.9 grams over X. Solve for X, and X equals 3.9 grams. 3.9 grams is the amount of drug that mimics osmotically 0.9 grams of sodium chloride. And since that's the amount you need per 100 mils, 3.9, that's per 100 mils, that's 3.9%. That would be the answer you would need for that question. This is and beforehand I told you I kind of wrote a question for the dilution that was as complicated as possible. This is as straightforward as it could be. So hopefully this one is an easy thing. It says 500 milliliters of a solution of a concentration of 100 milligrams per milliliter of drug is diluted to 2 liters. What is the new concentration? That is a dilution. It even says dilution in there. So hopefully it's fairly straightforward to say, well, I'm starting with a quantity of 500 mils that has a concentration of 100 milligrams per mil, and what I get has a quantity of 2,000 milliliters. What is the concentration? So in here I'm going to set X equal. The only little trick to this would be to make sure that we need to have the same units. So is milliliters the same here and here? Yes. So what was the concentration I was given in milligrams per milliliter? So I can keep that concentration, but I need to make sure that I remember that my X now represents the concentration expressed in what units? Milligrams per milliliter. So fine, let's just set it up because M1 equals M2. So 100 milligrams per mil times 500 mils is going to equal X milligrams per mil times 2,000 mils. Do that little bit of math, solve for X, and you get 25. But remember, 25 what? Milligrams per mil. And that's fine. I didn't tell you what to express it in. Had I asked what concentration, what percent concentration, would you agree you'd have to go a little bit further and change the 25 milligrams per mil to a percent concentration or something like that? But solving essentially the dilution in any units here, that's 25 milligrams per mil is the right answer. Okay, we only got 2 left here. We'll get them done, I think. So the recommended dose, this is just a concentration one. It says the recommended dosage for Somatram, which is a form of growth hormone. It's a variation of growth hormone. So Somatram is the normal dose 0.1 milligrams per kilogram, given either subcutaneously or intramuscular, which you could both do either of those, right? Yay, congratulations. 3 times a week. Somatram is supplied as Protropin brand name concentration of 5 milligrams per 2 mils after the reconcentration after the reconstitution. And again, somatrim, we said, isn't exactly hormone, but it mimics hormone and a growth hormone such that 1 milligram of somatrim essentially is the same as 2.6 international units of growth hormone. So the first question is, how many milliliters of atropine injection should this patient be given for a dose? And how much actual growth hormone is that equivalent to? So this is a dosing question. So start with the patient's weight. It was 84 pounds. Since the dose is weight-based by kilogram, we got to take the weight and convert from pounds to kilograms. So we'll divide it by 2.2 so that pounds convert to kilograms. And again, we were given this dosing scheme up here, so just bring that down. And essentially, this is the number of milligrams. All right. To convert the actual weight of the drug, or we need, to the volume of the injectable, we'll just take its concentration. We were given its concentration down here, set it up so that milligrams cancel, and I would get 1.53 milliliters of the injectable to get my 3.82 milligram dose. And the last part was say, okay, this dose, that's the dose of somatrim. How much growth hormone is that equivalent to? Well, I was told it's 2.6 international units per milligram of somatrim. So if I multiply that across like that, milligrams cancel, and I get 9.9 international units of growth hormone is what that's equivalent to. Last question here, and I'll try to do this quick. I like this one. This is kind of a good one as well, as far as it just takes a little bit to understand the information you were given. Because there's this patch, topical patch, Climera, provides estradiol. Instead of taking it orally, because it can cause a lot of side effects sometimes, and you take a higher dose to get it orally, then you can just put this estrogen on the skin. Let's do that. It comes as a patch. The patch lasts for 7 days. That's much more convenient than having to put one on and off every single day. So we got a 7-day patch. What do we know about this patch? We know that it releases the equivalent of, that is, into the blood, you get 0.1 milligrams of estradiol per day. So every day into the blood, I actually absorb a total of 0.1 milligrams every single day. I also know to formulate the patch that it has actually 7.6 milligrams of drug in there, because not all of the drug comes out of the patch. Some of the drug is there to kind of force it out of the patch and onto the skin. So it's got overfill. It's got 8% overfill. Okay, so this 7.6% represents the total amount, which has also 8% overfill. Okay, with all that information, what's the question? What is the percent absorption? How much estradiol from that amount of information, can you tell me what is the percent absorption across the skin? Okay, if I put 100 milligrams on the skin, how much actually gets into the blood? That's just the kind of question it's asking. All right, there's 2 things you need to know. You need to know how much total essentially drug was placed on the skin and how much total drug made it into the blood. Those are the 2 questions to answer that. So the first question about how much total daily drug did we put onto the skin is the total amount we put in the patch, the 7.6 milligrams, but we got to subtract that 8% overfill. So let's multiply the total 7.6 times 92%, which would reduce it by 8%. We got to reduce the total by 8%. So 7.6 times 92% essentially means that on the skin over the 7 days, it was exposed to 7 milligrams. 7 milligrams over 7 days were placed on top of the skin. Okay? How much drug actually made it into the blood? Well, we were told that the daily bioequivalent dose is 0.1 milligrams. So every day, the patient got 0.1 milligrams of this drug into their blood. How long did that patch last for? 7 days. So it takes 7 days times 0.1 milligrams per day. I would argue that this patient essentially had absorbed into their blood a total amount of 0.7 milligrams. So they absorbed 0.7 milligrams out of how much did we put onto the skin? 7 milligrams. So all you got to do is to calculate that as a percent. We want the percent absorbed, so the amount absorbed was 0.7 milligrams over the amount placed on the skin, which was 7 milligrams. Express it as a percent by multiplying by 100, and you see 10%. So 10% of what's placed on top of the skin actually gets through the skin and into the blood to be available for the rest of the body. So essentially this was a question not so much about math as reading the information you were given and trying to construct to the final answer here, which I think you've all realized at this point is probably still the hardest challenge for any of that stuff.